Um, in this video, we're going to work on some exercises related to convolution. And before we do the convolution exercises, let's look at one quite interesting result. It's what we call the even signal and the odd signal. So what exactly is the even signal, right? Here, xe minus n equals to xe n. So the folded signal equals to the signal itself. That's called an even signal. So if you fold a signal and you obtain a signal that's identical to the original signal before the folding, then this signal is called an even signal. It's basically a symmetric signal. So if the signal is basically symmetric with respect to the origin of n equals to 0, then it's called an even signal. And odd signal is what? Odd signal is that if you fold the signal, you get the original signal back, but with a minus sign. So if you fold the signal and the result is sort of the original signal multiplied minus 1, then it's called an odd signal. So odd signal is basically an anti-symmetric signal, right? It's anti-symmetric signal. So if you have studied even functions or odd functions before, when you were doing calculus, that kind of thing, then it's pretty much similar to even function and odd functions, right? Even signal is just a symmetric signal, and the even function is just a symmetric function. Odd signal is a anti-symmetric signal, right? The really interesting result is that for any signal, whether it's symmetric or not symmetric, you can always decompose it. You can always express the original signal, any signal, any kind of random signal, it doesn't really, into an even component and an odd component. So you can decompose any signal into a summation of an even signal with an odd signal. And the even signal, you can obtain the even component. You can obtain the even component by using this particular formula. Basically, you are just adding xn to its folded signal and then divide by 2. And therefore, if you want to obtain the odd component of this signal, all you have to do is to subtract the signal with its folded signal and then divide by 2. This way you can actually obtain an even component and odd component of any signal, right? But let's look at how we can actually sort of demonstrate this particular result, right? And I have an example. It's basically this example. So let's just decompose this particular signal. It's basically a boxcar, right? It's basically a boxcar. You're subtracting 2 unit step functions, and then the result is a boxcar, right? And it's not a symmetric signal, right? And it's not an anti-symmetric signal either. It's an arbitrary signal, but we can decompose it into a even and odd components. So let's try to write some codes for doing that. Let's just keep using our old script called s1.m, right? And but we are gonna add a new section to it. That's just for this particular exercise. And let's try to construct the signal n first. All right, the n. Let's assume a horizontal axis n for the x signal. Let's just assume n goes from like a 0 to 10, for example, with 11 points, and then x equals to step seq. We're gonna use our step function that I written before, and then the first one has a switch point from 0 to 1, it's a switch point at location 0, right? And then I'm gonna use a range. The range, let's just use 0 to 10, and then I'm gonna subtract step seq, another step sequence, and this time the switch location is at location 10, and then 0 to 10. So that's gonna be our x signal. Let's just execute this thing and then make a plot of it. So that's the x signal. basically a boxcar goes from 0 to 10, right? So if you want to change the horizontal axis, minus 10, minus 15 to 15, for example, and we can sort of see it's indeed a boxcar. Right? Now let's try to write a function. Let's try to write a function. The function called even odd xn. It takes an input, and then it's gonna do the decomposition into the even part and then the odd part together with a horizontal axis that's common to both the even component and also the odd component. So in this function, we're basically trying to implement this particular formula. But there's several things that we have to consider before. It looks like the formula is quite simple, right? It just involves a fold and then a sig add, right? Sig fold, sig add, right? Sig fold, sig add again. But let's try to sort of write this function and try to consider some possibilities, right? Some possibilities, and which might make this function slightly more robust. So that's what the function declaration actually looks like. And then the first thing we're going to do is to try to make sure that the input signal is indeed a real sequence, right? And we can do this kind of a check by using the any function and then the imag function. So basically, I'm taking the imaginary part of the x sequence and make sure that it's not 0. As if any of those imaginary parts is actually not 0, then I'm gonna report an error. I'm calling the Matlab error function and then report an error message. X is not a real sequence, and then we should just execute the function, right? So that's just for checking that the input sequence is indeed a real sequence. And then the thing that we need to consider is that once we fold the signal, the horizontal axis is gonna extend, right? The horizontal axis is gonna sort of the range of the horizontal axis is gonna change, right? So n is gonna be the horizontal axis of the input signal x, and then I'm doing a flip left to right, and then put a minus sign, which is essentially the same as the coordinate change that we did in sig fold. But here I'm actually assuming that the input signal is actually a row vector, so I have to sort of do a flip left to right. If it's a column vector, then I have to do a flip up and down, flip a UD actually. I have to call that function. Right. But here I'm not sort of doing that. But in your case, you probably want to just add another comparison just to make sure that it's if it's a row vector, you flip left to right, and if it's a column vector, you flip up and down, right? And then the m is gonna be the horizontal axis of the folded signal. And then what I'm gonna do in those lines is actually to construct a signal that has the horizontal axis extended to include the horizontal range of the flipped signal and also the horizontal range of the input signal. So m1 is going to be the minimum of both m and n. M is sort of the horizontal axis of the flipped signal, and n is sort of the horizontal axis of the input signal. And then m2 is sort of the maximum value. And then m is going to go from the minimum value to the maximum value for both m and n. Right? So m is going to be the horizontal axis of the extended signal, right? And then I compute a new number that's called nm. Nm is basically the difference between the first number in n and then the first number in m, right? It's the first number in n and also the first number in m, just subtracting them. Basically, nm is basically the offset of the first index in the input signal and then the first elements in the extended signal. And n1 actually is 1 to length m. I'm going to use n1 as the index, right? So here I'm actually constructing x1. x1 is the O0 vector with the length that's equal to the length of m, the extended signal, the horizontal axis of the extended signal, right? And then x1 n1 plus nm. Nm is the offset that I computed here, and n1 is sort of the range. N1 is sort of the range of the input signal, right? So n1 plus n equals to x. So basically, I'm assigning x to this x1 vector, the 0 x1 vector, right? And then assigning x1 to x. I'm assigning x1 back to x, right? And then xe is the even part of the signal. Here I have to sort of just implement this. I only need to sort of write down this formula. It's 0.5 times x plus flip left to right. Again, I'm assuming input signal is also a row vector, right? And then the odd part is just 0.5 x subtract flip left to right x, right? So that's going to be our function for doing the even odd decomposition, right? And then now let's go back to our example. Let's go back to our example, right? And then we're gonna work on the script. Let's try to write the rest of the codes by using the even odd decomposition. So here I can just call my even odd decomposition xo xe xo m is gonna equal to all I have to do is to call this function and then give it the input. The x is gonna be the input, right? And then n is gonna be the output, right? And then now let's try to make some plots. I'm gonna do a subplot. So here I'm gonna do 4 subplots, and then it's 2 rows, 2 columns. In the first subplot, I'm gonna plot the original signal. Rectangular pulse. And then mxe, that's the even part. Axis. I'm just gonna call xlim minus 10 to 10. What I say, it's the odd part. It's just around it. So that's gonna be the original signal. Maybe I should also change the range. I go back to the editor and then change the xlim minus 10 to 10. Right. So that's sort of the input signal, and then that's the even part, and then that's the odd part. So it looks like quite strange why the even part has a spike with a magnitude of 1 in the middle, right? The thing is that if you add the even part to the odd part, then all the sticks here it's a 0.5, right? And then all the sticks here is 0.5. Add them together, it's gonna be 1. And then this even part add to this spike with the amplitude of 1 add to this 0, it's gonna give you 1. So it's gonna recover this rectangular pulse, right? And then this is 0.5, and then this is a negative 0.5, and you add them together, it's 0. So it's gonna give you exactly it's gonna recover the input rectangular pulse. So that's even odd decomposition, right? But let's try to understand the convolution, right? Let's try to understand the convolution. And one of the results that I'm going to show you in this exercise is that convolution and correlation, in terms of the operation, it's actually related. So what I'm going to try to show you guys is that the correlation is convolution after folding. So here I'm actually computing correlation, right? So you can actually compare this formula with the convolution formula. The convolution formula we had here, k goes from it's a summation, right? K goes from minus infinity to positive infinity, and then xk. Then that's the impulse response, another signal, basically the other signal, h n subtract k. But we have to pay special attention to the index. Here is k, and then n subtract k, right? And then that's the correlation. Again, summation, k goes from minus infinity to positive infinity. So here I'm actually changing n to L, it's basically just another index. So it's k, you can treat L just as n, so it's k subtract L. Or if you think of L as n, it's k subtract n, right? Do you guys see the difference? It's k, n subtract k. Here it's k subtract n, right? Different. It's a different operation. But it's just one of the signal has to sort of the horizontal axis has to be flipped. It's basically a folding, right? It's basically folding. So if you actually do a folding on y signal, right, you can actually just you can convert y signal. This is a k subtract L, right? So if you actually extract the minus sign, right, then k subtract L equals to minus with a parenthesis L subtract k, right? And if you consider y minus this thing as some folded signal of y, then the equation becomes identical. It's xk y minus n subtract k, just like the folding, except that now you have a minus sign in front of it. So effectively, you can actually write a correlation as xl, so star means convolution. You're basically convolve with folded y, right? So mathematically, that's how you can actually manipulate those signals in order to actually write them in a similar fashion, right? In a similar fashion, but one of the signal has to be folded, right, before you actually do the convolution, right? So, but let's try to validate that. Let's try to validate this particular result. Now let's work on the convolution examples, right? Let's work on the convolution examples. So last time I was showing you guys I've written a function that's called conv underscore m dot m, right? And that was the function that I was showing you guys last time. It basically performs the Matlab convolution by calling the Matlab conv function, and then it also outputs the range of the output signal, the horizontal axis ny, and you construct the ny by using this kind of formula. That's the beginning and that's the end, right? The beginning index and index, right? So let's just try to use this conv underscore m function for a arbitrary signal. Let's just call this signal x equals to just putting some random numbers into it, 4, 2, for example, right? That's just a row vector. X is just going to be a row vector. 1, 2, 3, 4, 5, 6, 7 elements in it. And then the horizontal axis goes from say -3 to +3 for x, right? That's my horizontal axis. And then I'm going to convolve it with some other function. Let's just call it h. It could be an impulse response, or could be it depends upon how you understand it, but it's just the other signal. 2, 3, 0, -5, and then 2, 1. And then nh, the horizontal axis of the other signal, actually goes from let's just assume it goes from -1 to 4 or something, right? So if I want to convolve these two signals together, it's going to be y and y equals to conv underscore m, right? X and x h and H, right? And then that's it. And if you want to sort of make a plot of it, 3 rows, 1 column, right? And then we can just do stem nx x, and then x lim goes from like say so -5 to +5, for example, right? Just and then subplot 3 1 2 stem and h x lim -5 to 5, and then subplot 3 1 3 stem and y x lim -5 5. Right. Let's just execute this part. So that's the input signal. That's the input signal x, and then that's sort of the impulse response, and then that's sort of the result of the convolution. Right. And the range has to be -3 plus -1 for the output, right? And that's -4. And then it's gonna be 3 plus 4. That's gonna be 7, I think. So the output should have a range that goes from like -4 to 7. But unfortunately, I cut it at 5, so maybe I should just extend it to like 8. Right. 6 7. So last output point, it's 7. So that's basically a review of how to use the COMV function, right? COMV underscore m function, right? Let's try to work on some slightly more complicated exercises. Let's try to compute the cross correlation between signal y and xn, and then what's gonna be yn, right? Yn is gonna be xn subtract 2. That's gonna x shifted by like a fact by 2 positions, and then add some sort of random noise to it. Right. But we're gonna compute the cross correlation by using convolution. By using the convolution operation, right? So let's write a new section in the same script. I'm gonna keep using the same x and nx, but I'm gonna construct a new y signal, and then the y signal is gonna be shifted, a shifted version of the x signal by a position of 2, by a location of 2. So y and y is gonna equal to sig shift x and x, and then I'm gonna shift it by 2. So y is going to be a shifted version of x, and then w equals to rand n means a Gaussian or normal distributed random noise, and then the length of y, and then nw is going to equal to ny. Basically, the horizontal axis of the random sequence is going to be the same as the horizontal axis of the y sequence, right? And then ny equals to sig add. I'm going to use the sig add signal. It's y ny w and w. That's going to be our y sequence, right? Here I'm actually just reusing y and ny because I'm adding y and y to w and w, and then putting the result back to y and y. So I'm just reusing those same containers or same variables. But let's make a plot. Let's make a plot. Now, instead of 3 1 1, and then just a stem. -7 to 7, -7 to 7. 1 2 stem and y -7 7, and then subplot 3. I'm gonna use subplot, the third subplot later on after I finish the correlation. So how am I going to do the correlation? I'm going to use the convolution function, conv underscore m. But as what I was telling you before in this equation, before the convolution, you have to fold one of those signals. In this particular example, I was folding the second signal, right? But you don't have to. You don't have to fold the second signal. You can also fold the first signal, right? It's either one is actually gonna work because so here I'm gonna just fold x. I'm gonna just fold the x. So x n x equal to sigfold x n x, right? Again, I'm reusing the same variables. It's just the folded x. And then I'm gonna compute the rxy, and then its horizontal axis is rxy. That's gonna hold the output of conv underscore m. Then y ny x nx, right? So here I'm folding x, right? But I'm actually using x as the second input in the conv underscore m function. So what I'm actually trying to do is still trying to fold the second signal here. It's exactly the same actually. And then I'm gonna make another plot 3 1 3, and then stem and rxy stem goes from like -7 to 7. Right. Let's just run it. So this is actually the input signal, x. Right. That's the input signal. And then that's sort of the shifted version of x. That's the y signal, but with some random noise to it. So you can sort of see the shape looks quite similar to x, but the amplitude is not exactly the same. And you can sort of see that, right? You can sort of see the amplitude is not exactly the same. And it has been shifted to the right by a position of 2. It's been shifted by 2. And then the last trace, the last signal, is actually the correlation, but computed using convolution. Right. Correlation is a way for you to extract similarities between signals. So when these two signals are most similar, right? If you shift one of those signals, right? Suppose you shift x, you have to shift it by like 2 positions to the right to actually match, to get the best match with the y signal. So for the delay, so for the cross correlation, the horizontal axis actually means delay, right? And you can sort of see there's a maximum that's reached at position 2, right? So physically, it actually makes sense, right? Because it's indeed has a maximum correlation or maximum similarity at a delay time of 2, at a delay of 2, right? So this is how you can actually compute a correlation by using convolution, right? So this equation basically allows us to write our own cross correlation function by using the conv underscore m function that we have been using before, right? Here we are basically computing the correlation by calling conv underscore m. But before we do the convolution, we did a sigfold on one of the inputs, right? Matlab also has its intrinsic cross correlation function that's called xur. If you just type help xur, it's going to display the help page for the cross correlation function. But one of the things that's kind of inconvenient for this particular function is that it doesn't allow you to enter different horizontal axes for the 2 different input signals. Right? It's basically assuming these 2 signals actually has identical horizontal range, right? But the conv underscore m actually allows us to deal with the situation where the input signal has different horizontal axis or different range, right? So let's try to write our own cross correlation function, right? Let's just call it xur underscore m dot m, right? So here's how this function actually looks like. Here's what this function actually looks like, right? So that's the function name, xur_m, and then the first input, and then the second input, right? And then that's the output. Output is basically the correlation itself, and then the horizontal axis of the correlation, right? And then it involves two different calls. First, sigfold. You are folding the signal. You can fold either x or y, right? Here I'm actually just folding the first input, and then generate an output that's x1 and x1. That's the folded x. And then you're calling conv_m, x1 and x1, and then y and y, right? And then that's going to generate the output. Right? So basically, in our previous example, if we go back to our previous example, that's inside of S1, right? Now, once we have this our own cross-correlation function, we can sort of go back to our previous example and just replace these two calls with our new cross-correlation function call, just a one function call, right? So before we actually do that, we have to sort of make sure that we have an x, right? So for this section of the code, I was using the x that's constructed in the previous section, but if you have cleared out your memory, then you have to reconstruct it, right? Just to make this particular example more complete. And then let's just comment out these two lines, right? Let's just comment out these two lines, and then replace them with a call to our own xur_m function, right? And then x and x, right? And then y and y. That's it, right? And then let's just run it and see if it's actually giving us exactly the same result, right? Yes, they are identical, right? That's the x, that's the y, and then that's the cross correlation. Again, it has its peak at 2, right? But now let's look at what I was telling you before. If you sort of you can fold either the first signal or the second signal, right? But suppose we fold the other signal, right? We fold the other signal. So here I have commented out the two lines in my original xur_m function, in which basically I was folding the input x signal, right? And then do a convolution of using the input of using the folded x with y, right? Here I'm actually folding the second signal, y and y, right? And the output is going to be y1 and ny1, and then I'm doing a convolution of x and x with the folded y. You see, right? So here I'm actually doing a convolution of folded x with y, but here I'm actually doing a x with folded y. Why? So let's see what's going to happen. Here, that's the script. I didn't change anything in the script. It's going to be exactly the same call. Right? And then let's just run it. Let's just run this particular section and see what's going to happen. Now let's go back to the figure window. That's the input x, that's y. And the input signal x is identical to before. Y may have some slight differences because it's a random number. I'm adding random noise to it, so every time I run it, the random noise could be different, right? But its shape is kind of similar to x, right? But it's shifted by 2, so we can still think of y as kind of similar to before, right? But now the cross correlation, right? Do you guys remember where the peak was, right? The peak was at positive 2 before, right? But now the peak is at minus 2. You see, right? So depending upon which signal you actually fold, the peak of the cross correlation or the result of the cross correlation is going to be different, right? But they are actually symmetric. So if you for this particular example, if you actually sort of switch it back, you're going to get a similar result, except that the cross correlation is going to be symmetric with respect to 0, right? So if you don't believe me, if you actually let's try to hold on to the last subplot, right? Let's hold on to it. And then let's use a different color, for example. Right. Let's just run this line. Let's just run this line. No, let's just run this line by let's change the XOR function back first, right? And save it. And then let's run this line again. Run these two lines actually. So if you actually look carefully, it's actually two identical signals. It's just a sort of it's two symmetric signals, right? So here I have extended the range of the cross correlation a little bit. So here it actually goes from like -10 to 10, so you guys can see all the points, right? And you can sort of validate what I was saying. It's symmetric. It's symmetric, right? So if you actually fold the first signal instead of the second, you end up with another cross correlation, but it's going to be symmetric to the to the result from if you've actually folded the second signal instead of the first one, right? So that's sort of the first effect of the cross correlation. Right? The information is pretty much identical. There's no more information or loss of information. The information is identical. It's just you are changing the sign of the horizontal axis, which is basically the lag, right? So some people prefer to use if you think about cross correlation as shifting one of the signal and then try to compute the multiplication with the other signal, right? Shifting one of the signal. So which one are you shifting? You can shift the first one, or you can shift the second one, right? If you shift the first one, you're gonna move it to the right, right? And then the horizontal axis is gonna be the amount of shift of the first signal, right? You have to shift it by like a +2 in order to match the second signal, right? But if you actually shift the second signal to match the first signal, then the horizontal axis of the cross correlation is going to be the amount of shift for the second signal, right? And then you have to shift the second signal to the left, right? In order to match the first signal, right? So it's basically just telling you which shift. It just depends upon which signal you're actually trying to shift, right? So that's one of the things that you have to pay attention to. Which signal you want to fold, right? Which signal you want to fold. And there's also another property of the cross correlation. So let's go back to our example, right? Here I'm actually doing the cross correlation of x as the first input and then y as the second input, right? Here I'm going to keep the cross correlation function the same. I'm not going to change the cross correlation function. The cross correlation function is still as before, right? As before. So I'm folding the first signal and then compute the cross correlation of the folded first signal with the second signal, right? And but when I call XOR_M, I want to shift the first signal and the second signal, right? So so let's just do a different call. Instead of x and x, I'm gonna do y and y first, and then call x and x. Right? Oh, sorry, missed the parentheses. And then I'm gonna plot it in black. Again, let me change the range from -10 to +10. Right. So this time we're gonna compare black signal with the red signal that I was using before, right? The red signal. Right. Again, let's try to revalue these two lines just then. And then let's go back to look at it. So you can sort of see the black signal and the red signal are symmetric to each other, right? Again, that's sort of similar to what if we have changed the function body, right? If we fold the second signal instead of folded the first signal, right? And here you actually get sort of the same kind of effect by just switching the input and output, right? Switching the input and output order, right? And it's actually the same kind of effect. It's actually the same kind of effect, just like what I was describing. If you want to shift the first signal to match the second signal, or if you want to shift the second signal to match the first signal, right? The same kind of effect. You're gonna get a symmetric cross correlation, right? No, not symmetric cross correlation. You're gonna get a cross correlation that's kind of symmetric to if you actually switch the order of the two input signals, right? So the information is still the same. It just depends upon what's your preference, right? Do you want to shift the first signal or do you want to shift the second signal and hold the first signal constant, right? It doesn't really matter too much in practice, but it's just something that we have to pay attention to if you want to make sure that the delay time, the horizontal axis of the cross correlation, is consistent throughout all your analysis, right, for a particular problem. So that's kind of the relation between convolution and correlation, right? But now let's try to study some additional properties of convolution, right? The convolution operation has several very nice properties. First, it's a commutation. It's a commutable. So if you have two signals convolving with each other, the first signal and then the second signal, it equals to the second signal convolving first signal. So it's commutable. The operation is commutable. The same is not true for correlation, as you can see, right? In my previous examples, if you sort of switch the role of the first and the second signal in the XOR_M, you're gonna get a result, the correlation result that's gonna fold. That's the folded result of if you actually use the first input first and then second input second. So for correlation, you don't really have this commutation property. For convolution, you have commutation, and then you also have association. So if you convolve the first two signals first, and then convolve the result of the square bracket with the third signal, the result is the same as convolving the second and the third signals together in the square bracket, and then convolve the result with the first signal. This property is not applicable to correlation either. And later on, when we design filters, that kind of thing, or try to apply different operations on the signal, you're going to see the association property is quite useful for convolution. It's actually quite useful for convolution, right? And it allows us to combine different operations together into like just one operation. Instead of sort of applying multiple operations on the same dataset, all you have to do is to apply one operation on the same dataset, right? We're going to see its utility later on. Distribution. So if you have two signals added together and then convolve with the other signal, another signal, and then it's equals to carrying out this convolution individually and then add them together. And the last, very useful, is the identity. So you convolve the signal with an impulse that's been shifted. What you actually end up with is a shifted input signal, and the amount of shift is identical to the amount of shift that's in the delta impulse. So let's try to validate these four properties by using some arbitrary signals, right? So let's try to generate like three signals first, right? Again, I'm just reusing the same script. Let's try to generate some arbitrary signals. So let's try to generate the first signal. Its horizontal axis is called nx1, and it goes from -5 to 25. And then the x1, the signal itself, equals to cosine pi divided by 4 times n, and then dot multiply. I'm going to use a step sequence, step seq, and then the switch point is at -5, and then it goes from -5 to 25, the range. and then it's subtract another step sequence, and then the switch point is at location 25, and then the range is from -5 to 25. So that's going to be our first signal. If you would like to sort of, sorry, I missed a comma. If you would like to take a look at the signal itself, you can do a stem. There we go. Go to the figure. Clear off the figure, and then I can just do a stem on x1. Sorry, I missed. So that's gonna be our first signal. It's actually a cosine wave. It's a cosine wave, but it has a it is multiplied with a boxcar that goes from like a -5 to like a 25. I think goes from like -5 to positive 25. It's a boxcar, right? A cosine multiplying with a boxcar. That's our first signal. So let's do a subplot. 4 1 1 stem, right? Then xlim goes from like -10 to 30, for example. Right. So that's gonna be our first signal. And then let's try to construct our second signal. X2 equals to 0 to like 20, and then x2 equals to 0.9 dot hat on x2. So it's a power series, right? It's a 0.9 dot hat. So it's applying the power onto every element of an x2, right? So no. I mean, every element in every nx2, it becomes the power of 0.9 actually, and then dot multiply, another step sequence, steps seq, but a switch point at 0, and then goes from 0 to 20. Subtract the switch point at 20, 0 to 20. Subplot stem, and then I'm gonna use the same xlim. Looks like I typed something wrong. Step seq, right? So that's gonna be our second sequence. It's an exponential sequence, right? And then our third sequence, nx3 equals to -10 to 10, and then I'm gonna use some random sequence. So x3 is gonna equal to I'm gonna do a round 5 times rand n, size of nx3, I mean. So rand n is gonna give me a normally distributed random sequence, right? And then I use the Matlab intrinsic function round to round those floating point random numbers to integers. Basically, it's gonna be just a 0 or 1 or something, and then assign it back to x3. So that's gonna be my random sequence, right? Random sequence. So now let's try to validate the first property, right? x1 convolve with x2 equals to x2 convolve with x1, right? Commutation. So what I'm gonna do is do a y and y. So y1 and y1 equals to convm x1 and x1, x2 and x2, right? So in this convolution, x goes first, x1 goes first, and then x2 goes second, right? And then I'm gonna do y2 and y2 equals to conv underscore m, but this time x2 and x2, x2 goes first, and then x1 and x1. And then let's see if the result is identical, right? So plot 414. They're gonna do stem ny1 y1 using black, right? And then because I have to plot two things together, so I'm gonna hold on to my old plot, and then stem ny2 y2, but with a different color, red, right? So let's give it a try. x1. So go here. Rerun it. So that's gonna be the convolution result for first and second, right? And you don't really see any black signals. That's because the red signal is right on top of the black signal, so they are identical. So you don't see the black signals at all, right? And the range actually goes from like -5 to positive 45. You see. So if you the range of the convolution is sort of the range of the first signal, the first point of the first signal, -5 plus 0, right? It's a -5, and then 25 plus 20, like it's like 45, right? 45. So the range is also correct, right? So that's commutation. And then after you are done with plotting them together, you can sort of hold off. Association. So how do we actually compute the whole association, right? So on the left hand side, we have to convolve x1 with x2 together. So let's just call it y1 and y1 is going to equal to conv underscore m x1 and x1, x2 and x2, right? And now we have to convolve with x3. We have to sort of introduce another variable. So let's call it y left and left, not 1, and y left l. It's an l equals to conv underscore m. That's y1 and y1. Then x3 and x3, right? That's gonna be our left hand side. Now let's compute the right hand side. The right hand side, we need to compute the square bracket first, right? So let's just call it y2 and y2 equals to conv underscore m, right? And then x2 and x2, x3 and x3. So that's the stuff that's inside of the square bracket. x2, x3, x2 and x2, x3 and x3, right? And then yr and yr equals to, we have to sort of convolve x1 with the result in the square bracket. That's x1 and x1, y2 and y2, right? And then again subplot 414. Hold on. I'm gonna plot stem and y left, plotted in black, and then stem and yr, plotted in right, plotted in red, and then hold off. And then let's run it again. So again, you don't see any black signals on the bottom plot. That's because the red signals are right on top of it. So you don't see any black signals. Right. So they are consistent. Right. So that's association. That's association. Right. Now let's work on distribution. Let's work on distribution. This time you have to add two signals together, right? Add two signals together. Or distribution. So again, let's compute the left-hand side first. And we have to compute the stuff that's in the square bracket. That's adding x2 and x3 together. So let's just call it y1. And y1 is going to equal to sig add. Right? Sig add x2 and x2. Then x3 and x3. I'm just adding x signal 2 and signal 3 together. That's gonna give me the result in the square bracket. Now I have to convolve it with x1. So again, y left and y left equals to conv underscore m x1 and x1. Then y1 and y1. Right? That's my left hand side. Now let's compute the right hand side. So I have to do two convolutions now. To do two convolutions, one here and the other one here. Right? So I'm gonna reuse the signal y1 again. So y1 and y1 equals to conv underscore m, right? Then it's x1 x2, x1 x2 and x2. That's convolving x1 with x2, right? And then y2 and y2 equals to conv underscore m. This one has to convolve x1 with x3. So x1 and x1, x3 and x3, right? And then I have to add them together. Add signal y1 to y2, and I'm gonna call the result yr and yr. It's gonna sig add y1 and y1, y2 and y2, right? Again, I'm gonna reuse the force subplot. Hold on to it. Stem NYL, YL, black, and then stem NYR, YR, red, right? Then hold off. Let's just run it. So that's distribution, right? Looks like I've sort of plotted signals on top of each other. So that's that looks like I did something wrong with my hold off. Probably I should sort of, because I'm re-executing the same section again and again, so it's a problem. If I move it here. Let's see if that's going to fix the problem, right? Now it looks like it's giving me the correct behavior, right? So if you wanna sort of look at each example more carefully, you can use the Matlab command called pause. You can pause for a while, and then pause, and then pause. Right. Now let's rerun it. So that's the commutation. That's the commutation. The result is identical, right? And then that's association, right? Result from association. And then that's the result from distribution, right? So we have validated the A, B, and C relation, A, B, and C, right? Let's try to validate the last one. That's the identity, right? So identity. What's actually the stuff on the left-hand side? Left-hand side is convolving X with impulse, right? Here I'm just going to use say x1, we're gonna use x1 as x here. So on the left hand side, y left, y left. So I have to generate a delta impulse first. Sorry. So impulse sequence. So let's call it y1, and y1 equals to IMPSEQ, right? And then let's give it n0 some value. Let's call it n0. Let's just n0 equals to what might be a good amount. Let's just call it 10 or something. Let's just go 10. So n0 is 10. So n0, and then the impulse has to have a range, right? What was the range that we used previously? Let's go from like -10 to like 30, right? -10 to 30. That's gonna be our impulse sequence, right? So y left and y left is gonna equal to COMV underscore m, right? And then x1, I'm gonna use x1 and x1, right? And then y1 and y1. y1 and y1 is the impulse sequence. That's gonna be our left hand side. Now let's compute the right hand side. So yr and yr is gonna equal to 6 shift, right? I'm using x1 and x1, and then followed by the amount of shift. The amount of shift is n0, right? So again, let's try to use the full subplot. Let's just execute it. So it's gonna go back to the first commutation and validation, and then execute it one by one. So here you do see some black signals, right? But those black signals are 0, so it's sort of equivalent to sort of no signal at all, right? But for locations where you don't have any where you have non-zero amplitudes, the red signal is on top of the black signal. So here you sort of see there's no black signal at locations where you have non-zero amplitudes, right? So basically x1, that's the x1, right? We're shifting x1 by a factor of 10, I think, right? So n0 actually equals 10. So you're basically shifting the entire thing by 10. So -5 plus 10 is like a 5, positive 5, right? So the first non-zero is supposed to be at positive 5, right? It's about positive 5, right? And last non-zero is supposed to be like a 25 plus 10, 35, right? 35 here, right? So it's basically a shifted x, right? So you can sort of see convolution has some nice properties, right? Commutation, association, distribution, identity. So correlation doesn't have this commutation property. It doesn't have this association property, right? If you don't believe me, you can try. You can try, give it a try. But correlation does have this kind of distribution property. So if you correlate x1 with a summation of x2 and x3, it does equal to x1 correlated with x2 plus x1 correlated with x3, right? You can try. You can give it a try. Commutation and association by using exactly the same signals, right? You can just use the same signal that I have constructed here, x1, x2, and x3, right? And then you can just try it. So instead of COMV underscore m, you can do XCOR underscore m. For commutation, we have already tried it, right? If you actually switch the order of the first and the second signal, you're gonna get a correlation result that's the folded signal of the original correlation result, right? Before you actually do the switch of the two signals. And correlation doesn't have this association property. If you don't believe me, you can give it a try, right? You can give it a try. If you want to dig deeper, I can ask you what's gonna be the result if you do correlation in this way. What's gonna be the difference between the left-hand side and the right-hand side, right? What's gonna be the difference, right? Can you guys guess what's gonna be the difference, right? So now we have talked about the convolution and the correlation and their relations and their properties, right? So now let me ask you one question. Under what kind of situations convolution and correlation will give you identical results? Right? What kind of signal, what kind of input signal will actually give you identical results for convolution and correlation? So x1 and x2, you have two signals, right? You put them into conv underscore m, and you get a result, right? And then if you put the same two signals into xcor underscore m, and then you would get the same result as you got from the convolution. What kind of signal will actually give you that kind of result, right? So can you think of a situation that you would get a convolution result that's identical to the correlation result, right? Let's still go back to this particular equation. What I was saying, correlation is convolution after folding. So if you fold one of the signals and then do a convolution, then you get the correlation back, right? So what kind of signal will actually give you identical result for correlation and then for convolution? You see, here is the convolution operator, right? That's a convolution operator. But one of the signal has been folded. That's y minus l, right? So suppose y is a even signal. It's a symmetric signal. Then the folded y is identical to the original y, right? And in that case, y minus l equals to yl. And then you are basically doing what you are actually doing is xl convolve with yl, right? So in that kind of situation, you get correlation that's identical to a convolution operator, right? So let's try to validate that. Here I've cleared out my figure window, right? So now let's try to do some validation. So the first thing I'm going to do is to construct a even signal, right? A symmetric signal. Let's just call it x equals to this sequence of numbers. You can see the amplitude is actually symmetric according with respect to 1, this center point, right? And then that's my x, and then that's my nx, the horizontal axis. So it goes from like -3 to +3, right? If I want to make a graph of it, I can just stem nx x, and then I'll adjust the range of the signal. So suppose x lim goes from like -6 to 6 or something, right? Or -10 to 10, right? That's my symmetric signal. One of the input signals. It's a symmetric. And now let's construct another signal. Let's just call it y. And this time I'm just gonna do like 3 random sticks. 1 row, 3 columns, and then ny equals to just goes from like 0 to 2, and then subplot ny y, right? And then let's use 2, right? That's gonna be the other signal that we're gonna experiment with, right? And then let's try to call the convolution code. So the convolution code, I'm gonna call the result z, and nz is gonna equal to conv underscore m x nx, right, and y ny, and then I'm gonna plot nzz in the third subplot. So that's gonna be the convolution result, right? Let me hold on to it, and then now let's compute the correlation result. If you go back to look at my correlation code, x nx, y ny, so x comes as the first input and then y as the second input, right? So what I did in this particular code is that I folded the first signal. I first folded the first input signal, x and x, and then I got x1 and x1, right? And then I did the convolution for using x1 and x1 with the second input y and y, right? So now let's call this correlation function, but I'm gonna use x, my symmetric signal. I'm gonna use this thing as the first input signal, right? Because I know that for this even signal, after the folding operation, it's identical to the original signal, right? X1 and X1 is going to be identical to X and X actually, right? So I'm going to use C and NC to hold the result, and then XCOR underscore M. The first signal, that's the even signal, X and X, and then the second signal, Y. So the first signal, and then the second signal, right? And now I'm actually calling the correlation code. I'm doing a correlation, right? Now let's try to plot the correlation on top of the convolution and see if they are indeed identical, right? And I'm going to use a different color, subplot, right? And I have to hold on to the, I think I already did that, but just to make sure, right? So NC and C, right? And then I'm going to use a different color, say red. I'm going to use red. So if they are identical, I should not see any blue sticks anymore, right? Let me just type it. And that's indeed the case, right? So the red signal is completely on top of the blue signal, right? So in this kind of situation, correlation and convolution give you identical results, right? So if one of the signal is actually symmetric or even signal, right? So that's what I wanted to talk about the correlation and convolution and their relations, right? Don't forget these properties about convolution. So convolution, you have this kind of relation, right? Commutation, association, distribution, identity, right? And for correlation, these two conditions may not be true. Unless what? Unless one of the signal is actually an even signal. In that case, convolution equals to correlation, and you might get those results for correlation. But in general, convolution and correlation doesn't have these two properties. It doesn't have these properties either, right? Correlation in general, right? But convolution actually has those properties, right? And if you are just considering the time domain representation of convolution and correlation, then this exercise will give you some understanding about what those things are and what those operations are and their properties, right? And if you actually know about Fourier transform, if you know the frequency domain representation of signals, then you have a different perspective about convolution and correlation, right? For example, for convolution, the convolution frequency domain representation of convolution is essentially multiplication, right? So multiplication has these kind of commutation properties and association properties and distribution properties, right? That's why you have these properties for convolution, right? Because in frequency domain it's essentially multiplication. But for correlation, the frequency domain representation of correlation actually involves conjugation, a conjugation operation on one of the input signals, right? And depending upon which one you're actually conjugating, you could get a different result, and the kind of difference in the different results just depends upon which signal you are actually conjugating. So you could get a correlation that looks sort of the folded version of the correlation obtained using if you actually put the conjugation on the other signal instead of the one that you picked for the previous example. So once we have studied the Fourier transform, we'll get a different perspective about these two operations. And one thing that we have to sort of remember is that they actually represent quite different physics actually. So correlation is a way for you to extract similarities between two signals, right? So it's a way for you to sort of examine if a signal contains some kind of template signal or some kind of a smaller templates that you can actually match with, right? But convolution is essentially the output of a linear time invariant system. If you think about one of the signal as the impulse response of that linear time invariant system, right? So physically, in practice, you may interpret these two operations in two different kinds of a physical context. And their operations are actually related, right? And the relation among them can be understood in different ways, right? And so that's what I wanted to talk about convolution and correlation.